So this last lesson is going to be on something that we call intermolecular forces or interparticle forces. And so far we've only talked about the bonds, and that is the bonds that are holding one atom to atom. What we're going to talk about today is holding a molecule to a molecule. So let me recap real quickly. Of course, metallic bonds are our electron C, and so they are sharing their electrons amongst themselves. They do happen to be the strongest of the bonds. They have a very high melting point. Ionic bonds, of course, are transfer of electrons, and so we have a full-out positive and negative charges, and those are held together by that electrostatic attraction of the positive and negatives. And then, of course, a covalent bond, they're sharing their electrons, and so because of that, they're not always sharing equally. So we have nonpolar, which is a sharing of equalness. I don't even know if that's a word. And then, of course, a covalent polar is when they are sharing them unequally. And so what we're talking about today is intermolecular forces. So I want to be sure that you understand that what we're talking about today is not a true bond. It's what holds one molecule to another molecule. We don't have to talk about it with metallic bonds because they're held together by the electron C. Ionic bonds are held by the electrostatic attraction, and it's a crystal network of positive, negative, positive, negative. But when it comes to covalent bonds, what holds one molecule to another molecule? In other words, how do we have liquid water or solid water? Because it has to be holding those molecules together. So that's what today's lesson is going to be talking about. So when we are talking about intermolecular forces, we are talking about between covalent compounds only, okay? And they are the forces of attraction between the molecules, not the bonds themselves, but between the molecules. They vary in strength, but they are weaker than the bonds that hold those atoms together. So when we're talking about phase change, like when we talked about physical changes, we can go from solid to liquid to gaseous water. Well, we know that when we are boiling water, we are not breaking apart the bond of oxygen to hydrogen itself. We're breaking apart what we call these intermolecular forces that allow one water molecule to separate from another water molecule and then become a gas and go out into the atmosphere. Okay, so they are between covalent compounds only, and there are three types. The strongest of these is going to be between these polar molecules, and we'll see why in just a moment. So the first type that we're going to talk about, oh, by the way, you can abbreviate intermolecular forces with IMF. And the first one we're talking about is called dipole forces. And what this is the positive end of one dipole is attracted to the negative end of the dipole on the neighboring molecule. So they have to be near each other. And so the dipoles, of course, are these equal but opposite charges, slightly positive, slightly negative, that are separated by that short distance, and they are caused by the unequal sharing of the electrons. And so if we go to the hydrogen-oxygen bond, say in water, so we have water and we have hydrogen-oxygen bond here, we have hydrogen-oxygen bond here, what happens is the one with the highest electronegativity gets the electron more. So this side is going to be slightly negative, and this side is going to be slightly positive because it gets the electron less, so it's going to have those slightly positive. The other way we can show those forces, let's say I have HCl, which is a covalent compound. This side is going to be slightly negative because it is getting the electron more. This side is going to be slightly positive. We can also show those with these vector arrows. And so when we show that, we're showing that this is the dipole, that this side of the molecule over here is slightly negative. This is where the electron is going towards, and then the other side is going to be slightly positive. So because these molecules have these opposite but equal slightly positive negative charge, they are attracted to the opposite in the nearby molecule. So here we have HCl showing the dipole-dipole force. We always indicate the true bond by the solid line. So that is the true bond. In that case, that would be polar covalent because of their electronegativity difference. We indicate the IMF by this dashed line because it is not as strong. And so the stronger that IMF, the higher the boiling point, the higher the melting point, that sort of thing. So that is a dipole-dipole force, okay? We could have also indicated that dipole with these vector arrows if we had wanted. a type of dipole-dipole. It's often listed as its own type, but in fact, it is actually a type of dipole-dipole. It's a special type of dipole-dipole, and that is called hydrogen bonding. Hydrogen bonding is when hydrogen is present with a highly electronegative atom. And what happens is, it's a little bit different because it's not attracted to the slightly positive, slightly negative. It's actually attracted to the lone pairs on that nearby electronegative atom. It only occurs in 3 elements that are able to do that, and they are the most electronegative elements, and that is nitrogen, oxygen, and fluorine. Fluorine, of course, being the most electronegative. Several years ago, we came up with this little thing to help us remember that hydrogen bonding only happens with no orange friends, and that just helps us remember it. Sometimes people say hydrogen bonding is fun, like fun, to remember the 3 things, but those are the only 3 things that have hydrogen bonding. So I want to show you what that looks like in water, because hydrogen bonding in water is incredibly important. It's why hydrogen has a very high melting point, very high boiling point, because of those strong intermolecular forces. Generally, the more massive something is, the higher the boiling point. So if we were to look at H2S, which would have very similar properties, it has a much lower boiling point than water because of these hydrogen bonds. So hydrogen bonds are why water has this high boiling point. So responsible for high boiling point of water is hydrogen bonding. It takes a lot of energy to break those hydrogen bonds. The third type is called London dispersion forces. We can abbreviate that LDFs for short, because that's a lot of words to write and say. So what an LDF is it happens only, well, that's not true. It happens in all of the molecules, okay? They act on all of the molecules, but it is the only one to act on nonpolar. So I want to make sure you understand that, because sometimes people think that London dispersion forces are only in nonpolar molecules. They're in all of the molecules. They happen. It just so happens that the dipole or the hydrogen bonding that are present are stronger in that molecule than the LDFs. But for what happens for the nonpolar things, of course, they're sharing their electrons equally, but they're always in motion. And so they're creating these instantaneous dipoles. They're there and they're gone. They're there and they're gone. So I have a visual of that right here. And so those fluctuations in the movement cause these dipoles that are like they're instantaneous, meaning they're there for a short second and then they're gone. But because of that, they do have these attractions. Now, the interesting thing about a London dispersion force is in small molecules, it's a very weak force, okay? And we list it as the weakest of the dipole forces. But interestingly enough, when molecules get very, very large, that dipole-dipole force becomes much more important and becomes stronger, because the more electrons you have, the more movement, the more of these instantaneous dipoles you have. And so if you would look at the halogen group, we have fluorine, and then we have chlorine, and then we have bromine, and then we have iodine. Chlorine and fluorine are both gases. This is a liquid. And then lastly, we have a solid. And they are all nonpolar molecules, so the only thing they have acting upon them is these LDFs. But iodine has a whole lot more electrons, 53 to be exact, versus fluorine up here, which has 9, and then chlorine has 17, and then have 35. And so what that tells us is as this molecule gets more and more electrons, these LDFs get quite a bit stronger, so that in its natural state, iodine is a solid, and that is because it has relatively strong LDFs because of so many electrons. So I want to make sure you understand that. Okay? So what are the effects on these IMFs on the states of matter? Remember, when we're talking about IMFs, intermolecular, sometimes you'll see them called interparticle forces. We are talking about only covalent compounds which are sharing their electrons. Okay? So if they have very weak forces, they're going to be a gas. They're going to have low density, easy to expand and compress, and they're going to fill the container. If they have an intermediate intermolecular force, they're going to be high density, hard to expand or compress, and take the shape of their container. So that's an intermediate right there. And then lastly, solids have very high density, okay? They're hard to expand or compress, rigid, and then they would have the strongest intermolecular force. So when we did our lab on ionic versus covalent, we looked at the ionic compounds. They had high melting points, they dissolved, and of course they conduct electric current. But when we talked about our difference between our two covalent, we were trying to determine whether it was a polar or non-polar. And I don't know if you remember that when you started that hot plate, D, which ended up being non-polar, melted very, very quickly. Okay, and the other one that was polar, it melted. It just took it a little bit longer because it had stronger intermolecular forces than did the one that was non-polar. Okay, so some of the other responsible properties, such as flow rate, or something we call viscosity. And viscosity, of course, is basically kind of how thick the liquid is. Its official definition is resistance to flow. So something like syrup, very thick, has high viscosity, versus, say, rubbing alcohol, which is very thin, has a very low viscosity, and that's because of their interparticle forces or their intermolecular forces. Surface tension is another one. Surface tension is responsible for why bugs can float on water, because at the surface of that, what happens is those particles pull in closer to each other. We already talked about melting and boiling point being dependent upon. The stronger the interparticle or intermolecular force, the higher the boiling and melting point. Vapor pressure of a gas is also dependent upon that. Vapor pressure is the tendency of a gas to become a liquid. From a liquid to vaporize very quickly. So, for instance, gasoline has a very high vapor pressure because it very readily becomes a gas. So it has very weak intermolecular forces. Gasoline in itself is nonpolar, so it only exhibits those LDFs, and so it vaporizes very easily because of those London dispersion forces, those weak forces. Okay, so to summarize, I told you I was going to try to make this lesson as quick as possible. We were going to arrange these in order that would vaporize, meaning becoming a gas, most readily. And so what you want to do when you're trying to figure out something like that is you want to figure out what are their intermolecular forces. So water, of course, is H2O, and that is hydrogen and oxygen are bonded together. So that is definitely has hydrogen bonding because it is one of the things that can hydrogen bond. We have hydrogen present and we have oxygen present, so we do have that hydrogen bond. So to be clear, I don't think I stated this, for hydrogen bonding to happen, hydrogen has to be attached directly, I think I left that out, directly to the no orange friends, okay? If it's just present, like we might have something that just has some nitrogen present, just has some oxygen present, but unless that hydrogen is attached directly to that nitrogen, oxygen, and fluorine, it will not have hydrogen bonding, okay? So we have hydrogen bonding present here. This is non-polar, so we're only going to have those LDFs present. And then alcohol is telling you that it's polar, and so that's going to have that dipole forces. So the way that we would rank this, and it says arrange in the following which would vaporize the most quickly. B would be the most quickly, followed by C, and then lastly it would be A. Okay? All right, that is the conclusion of the lesson. Look at there, I made it under 14 minutes.